Hi, I'm Bill Kuszmaul, and this talk is for the paper on the optimal time-space trade-off for hash tables. Okay, so just to make sure we all start on the same page, let me just start by reviewing what a hash table is. A hash table is just a colloquial term that we use to refer to any randomized data structure that solves what's known as the unordered dictionary problem. What that means is that the data structure stores a set of items. These items are typically referred to as keys. Each item is W bits, so you can think of W as being the machine word size, and we'll use N to denote the number of elements that we're storing at any given moment. And then the set of operations that a hash table has to support are insertions, which add a new item into the hash table. For example, here we are adding the element 680 to our hash table. Deletions, which remove an item from the hash table. And then finally, queries, which check whether a given item is in the hash table. For example, a query of 353 would return yes, but a query of 112 in this example would return no because 112 isn't in our hash table. And then one more thing just for intuition is that we typically think of the machine word W as being theta log n. So the size of the machine word is theta log n. But our results in the paper won't actually require that. It's just kind of nice for intuition. Okay, so we're going to be talking a lot about time efficiency in hash tables. And so there's a few conventions that I want to set out. So first of all, for all of the data structures we talk about in this paper, we're going to require that queries be answered deterministically in constant time. So queries just have to be worst case constant time. And then when we're talking about insertions and deletions, we're going to always clarify whether the time bound is either in expectation or with high probability. But just to kind of keep things simple, let me just mention that all of the time bounds that we prove in this paper will be with high probability. And then, of course, the other subject of this paper is going to be space efficiency. So here's how you should think about space efficiency in a hash table. If you're storing n keys that are each W bits, then you can think of the amount of space that the hash table takes as consisting of two components. So the first is log of 2 to the W choose n bits. That's the amount of space that just information theoretically any hash table has to consume. And then the second term in the space usage is r times n bits for some quantity r. And the way to think about this quantity r is that this is the number of bits that we're wasting per key when you compare to the information theoretic lower bound for the space efficiency of a hash table. And so the central question that researchers have kind of focused on when it comes to space efficiency is how many bits must we waste per key in order to have a hash table with constant time operations. So there's been a long line of work on this topic, and the state of the art, which was proved around 20 years ago, was proved by Raman and Rao, who showed that actually you can do a pretty impressive bound. So you can actually achieve order log W wasted bits per key. For example, if W is order log n, then this is order log n wasted bits per key. And you can do this with constant time queries and with constant expected time insertions and deletions. That's what was proven in 2003. And there's been a whole bunch of subsequent work getting this to the point where now we know how to do the insertions and deletions not just in constant expected time, but also with high probability and with the same bound on the number of wasted bits per key. That's the state of the art for space-efficient hash tables. And while there's been a lot of work on trying to kind of get these bounds to be worst case, what there hasn't been is any further improvements on the number of wasted bits per key. And actually, what we've seen instead is over the past 2 decades, there's been a whole bunch of closely related problems where we've been able to get lower bounds showing that actually log W wasted bits per key is optimal. So examples of this include the dynamic retrieval problem, the question of maintaining dynamically resized filters, the problem of constructing a stable hash table, And what we see in each of these problems is that the bound that we get a lower bound for is the same bound for what we know how to do for hash tables. But nonetheless, it's remained an open question, is this bound of log w wasted bits per key actually optimal? Or is it possible to do better? So that brings us to the first main result of this paper, which is we show that actually you can do quite a bit better. So here's our result. We say, consider any parameter k. And as I mentioned before, our queries are going to be constant time, but now our insertions and deletions are going to be order k time, and that's a with high probability bound. Then what we can achieve with order k time insertions and deletions is that the number of wasted bits per key drops to log of log of log k times of n, so the kth iterated log of n. This is a pretty neat result because, for example, even if we set k to be order 1, we can drop the wasted bits per key to log of log of log of etc. of n for any constant number of logs that we want. So we get, significantly improved space bounds even in the constant time case. And then, on the other hand, if we want to reduce the number of wasted bits per key to constant, we can do that with just log star time per insertion and deletion. It's worth noting that there's some ways in which this is actually a pretty robust result. So for example, this hash table actually also dynamically resizes. So what that means is that its current space usage at any given moment is bounded in terms of the current value of n, the current number of keys in the data structure. Another thing worth noting is that this hash table is compatible even with the case where your machine word size w is very large. So in fact, the only constraint is that w should be at most subpolynomial. And so even with dynamic resizing and even with kind of lots of possible options for what w could be, we get this really steep trade-off curve between time and space. In fact, the second result in the paper is that this trade-off curve is actually optimal for a large class of hash tables. So I'll define what that class is in a little bit more detail later on in the talk. But let me just say for now that this class includes all of the known succinct hash table designs that we've seen so far in the literature. So what this means is that either this space bound is really optimal, or if we want to beat it, we're going to have to come up with fundamentally new ways to store data. Okay, so those are kind of the main results in the paper. And before I dive into the details for where they come from, I want to talk about one kind of surprising application. So this application is to another type of data structure known as a filter. And the way to think of a filter is that it's just a fixed capacity hash table, so it has some bound on the number of keys that it can store at any given moment. But the difference between a filter and a hash table is that there are false positives. What does that mean? Well, queries that were supposed to receive an answer of yes, they still receive an answer of yes. But if a query was supposed to receive an answer of no, now what's going to happen is the filter guarantees that it will respond no with probability at least 1 minus epsilon, but with some small false positive failure rate, epsilon, you'll actually get an answer of yes, even though the answer should have been no. So a filter is a hash table with rare false positives. So why are filters an interesting data structure? Well, they let you get even more space efficiency. So the way to think about the space efficiency for a filter is that there's an information theoretic lower bound on the number of bits that you need. So here this lower bound becomes n times log of epsilon inverse. Remember, epsilon is your false positive rate. And then again, you have some number r of wasted bits per key. And the reason that this is a cool bound is that it's typically much smaller than the amount of space it would take to store your items in a hash table. So you should think of the quantity log of epsilon inverse as being little o of log n. And so that means that this data structure can actually use as few as little o of log n bits. That's why kind of practitioners filters are so widely used in practice. But the question that we still don't know the answer to, or that at least we haven't known the answer to until now, is how small can we make R? Is it possible maybe even to get order 1 wasted bits per key? So it turns out we can apply our hash table result to constructing a filter. So there's a pretty straightforward application that gets you kind of the following result, which closely mirrors the result we had for hash tables. We can say, well, if we're willing to spend k time per insertion and deletion, we can get the wasted bits per key down to kth iterated logarithm of n. So that's a pretty nice bound, but it's very far from achieving what we really wanted, in the sense that if we want to get this down to order 1 wasted bits per key, we would need k to be roughly log star of n. And so the question is, can we do better? And surprisingly, the answer ends up being yes. So we're actually able to get down to order 1 wasted bits per key, and all we have to do that is add one small constraint on the parameter epsilon. So you'll remember that I mentioned that in most applications of filters, you should think of the quantity log epsilon inverse as being relatively small, being little o of log n. And so here we add a constraint that formalizes that. We say, okay, suppose log of epsilon inverse is less than log n over log 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 for any constant number of logs of n. Then it turns out we can actually get constant insertion deletion time, constant query time, and we can achieve a wasted bits per key of log base 2 of e plus little o of 1. So we actually get down to order 1 wasted bits per key. And it's worth noting that this is actually the optimal constant, at least for a large class of filters. So essentially, all modern filters that support insertions, deletions, and queries, they all use this idea of kind of storing a fingerprint of a key in a data structure. And it turns out if you do that, then you're forced to have at least log base 2 of e wasted bits per key. So we actually get to the optimal bound. And part of what's cool about this result is it doesn't follow directly from our hash table results from earlier in the talk. But instead, it follows from using those super space efficient hash tables as kind of algorithmic building blocks in a larger data structure. And so by doing that, that's how we're able to get filters that waste only a constant number of bits per key. Okay, so at this point, I've finished summarizing the results that I wanted to tell you about. And in the rest of the talk, what I want to do is tell you a little bit about our techniques, and also, in doing so, have a chance to tell you, kind of in a more formal sense, what the lower bound is that we proved. And just to kind of keep things simple for the rest of the talk, for now on, I am going to assume that our machine word size w is in fact theta log n. And that's just a kind of for simplicity of exposition. Okay, so if we're going to be talking about how to do space-efficient hashing, we should start with the classic technique that people were using in kind of the 1960s and 70s, known as open addressing. And the way that this works is that each key x has a sequence of positions where it's willing to go. In particular, you can think of these as being kind of hashes of x. So it has a position h1 of x that it would be willing to go, h2 of x it would be willing to go, h3 of x, and so on. And the catch is that if you put it in position hi of x, then if later someone queries x, that'll take time order I. And that's just because what's going on is in an open addressing hash table, the hash table first checks position h1, then h2, and h3, etc., until it gets to the position where x is stored. So that's a classic hash table design, and there's lots of examples of this. So for example, linear probing is an example of this. Here, h1, h2, etc. are just consecutive positions in the hash table. Cuckoo hashing is another example of this, uniform probing, etc. So that's classical open addressing. But you'll notice it really kind of isn't super compatible with what we're looking for, because we want our queries to be deterministically constant time. And if you want to get space-efficient open addressing, you don't get that, because you end up having large values of I for the hi of x position where x is stored. So it turns out what all known succinct hash tables do is they do kind of an interesting tweak on this. So modern hash tables actually consist of two data structures. The first is a storage array. That's where the keys are actually stored. And it turns out there's a little bit more magic going on where you manage to take off some of the bits of each key. But just think of the storage array as being the array in which the keys are stored. And you make the storage array be only a little bit bigger than the number of keys that it's going to store. So n times 1 plus 1 over log n slots. So this makes sure that our storage array is really space efficient. And within the storage array, you can think of it as being that we're still using open addressing. So each key x is still being stored in some position hi of x. But queries can't afford to just check h1, h2, h3, etc. So what we have is a second data structure that I'll refer to as the query router. And what the query router does is if you give it a key x, it'll tell you the value I so that you should go look at position h sub I of x. So for example, in this case, x would give you 3 because we're at h3 of x, and y would give you 7 because y is at h7 of y, and so on. So we refer to this as augmented open addressing because you're augmenting an open addressed hash table with another data structure that we call the query router. And this is the basic framework that has allowed for us to get to succinct hash tables in the last few decades. And I want to zoom in on kind of one of the central problems that you face if you want to make this data structure space efficient. So for each element x, if we store it in position h sub I of x, then let's define the probe complexity of that element to be the quantity 1 plus log I. So it's the number of bits, basically, that it takes to store the number I. Why do we care about probe complexities? Well, our query router actually has to store the number I. And so what that means is that our query router has to use at least the probe complexity number of bits per key. And it turns out this is actually tight. So one of the results we prove in the paper is you can construct a constant time query router that uses space proportional to the probe complexities of each key. And so what that means is that if your goal is to be space efficient, if you want your query router in particular to be space efficient, then the challenge becomes how do you minimize the average probe complexity of the keys in your data structure? And that's the problem that I want to zoom in on for the rest of the talk. So for this probe complexity problem, we prove two results. The first is an upper bound, which is essentially the same upper bound we've been talking about throughout this whole talk. What it says is that if you're willing to move around k items during each insertion and deletion, so what that means is that the insertion leads to k different items being rearranged in the hash table, then you can achieve an average probe complexity, which is log, 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 etc., k plus 1 times of n. That's the upper bound. And then the lower bound says that this is actually an asymptotically optimal trade-off curve. So in other words, this is really the right answer to the probe complexity problem. And as a consequence of this lower bound, we also conclude that any augmented open addressed hash table has to waste at least the same number of bits per key asymptotically as we waste in our data structure. Okay, so let's zoom in on this upper bound. Where is this coming from? Why do we get so much power out of just doing kind of a few moves of items around in the hash table? And to see that, let's start by considering the setting where we don't move any items on each insertion and deletion. So then what's the best thing you can do to minimize probe complexity? It turns out the best thing you can do is the following. Break the storage array into bins of size polylog n. And for each record x, define its probe sequence to just be the slots of some random bin in the data structure. And what happens is that when you insert a record, it goes to the bin, some random bin, and then we'll just put it in an arbitrary free slot in that bin. So the record's probe complexity could be any number that's order log log n bits. But the nice thing is that because of how balls and bins behave, with high probability, none of our bins overflow. And so what we end up with is a situation where every record really does have probe complexity order log log n. And it turns out this is actually optimal. So if you're not going to move any items around once you put them into the data structure, this is the asymptotically optimal probe complexity. And this is also one of the reasons why all of the past succinct hash tables have needed to incur order log log n wasted bits per key. So then the next thing I want to show you is why we can actually do much better even if we're just willing to move around one item per insertion and deletion that we do. So I'll show you how by doing one extra move, we can actually reduce our number of wasted bits per key down to order log 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 n bits instead of log log n bits. And when we think about moving elements around in a hash table, kind of the first thing that comes to mind typically is cuckoo hashing. But if you think about it, that's kind of, cuckoo hashing really isn't getting at the goal of what we want here. We really want something that's specially designed to reduce probe complexity. And it turns out the way to do that is the following. So what we're going to do is we're still going to have bins of size polylog n, but now we are going to break each of those bins into mini bins of size polylog log n. And what happens is each item has some mini bin where it would really like to go. If it can go in that mini bin, then its probe complexity is going to be order log 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 n. But then a small fraction of items don't end up getting to go into the mini bin that they want to go. And what those items do instead is they pick some arbitrary free slot in the larger bin that contains the mini bin. And so in that case, the item's probe complexity is log log n. But the insight is that we can move items around in such a way so that at any given moment, there are very few total elements that have this larger probe complexity that didn't fit into their mini bin. And so the result is that the average probe complexity is still just order log 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 n, the same as if everyone had managed to fit into their mini bin that they wanted to fit into. And so that's how, by just moving one extra item around on each insertion and deletion, you can actually get to a situation where you've exponentially reduced the probe complexity. And of course, you can recursively apply this idea, and that's kind of how we managed to get a small probe complexity for the data structures in our paper. Okay, so that's just a few of the basic ideas that show up in our data structure. And let me conclude by just commenting on some of the other kind of interesting technical challenges that we encounter in this paper. So one of them I already mentioned is, how do you actually build the query router so that the amount of space that it takes is just a function of the probe complexities of the keys? Another big problem is dynamic resizing. How do you adapt as the size of the data structure changes? And doing that without introducing additional space overhead ends up being a really interesting technical challenge. And then finally, there's the question of how to prove the matching lower bound for the probe complexity problem. And that ends up being kind of one of the big technical pushes in the paper. So one of my hopes is that maybe the ideas that show up in this data structure will also be useful for other related data structures problems. And so if you're interested in this kind of thing, feel free to take a look at our paper, and I'd also be happy to chat. Thank you very much.